Okay, so that's what we're dealing with. Complex numbers 2011. The A part of the question, you're told find x and y such that. See, I'm going to talk about this. Now, as an A part, it's a fairly handy question. I think probably the easiest way, or the easiest thing, is that effectively what this is, it's 3x plus 4y is equal to 20. That's one of the equations. And 5x plus 6y is equal to 32. And then it's just a simultaneous equation. So there's nothing difficult about it. These kind of questions do come up in B parts sometimes. And when they come up in B parts, you're often told using matrix methods. Now, if you use the method that I have just shown you there, you will not get any of the marks. The only reason this method, the simultaneous equation method, can be used is because you're not told how to do the question. So just be aware of that. Right? There are instances where you would have to solve that question using matrix methods. If you were going to do that, well, basically what you'd be doing is, not x over y, just xy, the matrix xy would be equal to the inverse times 20 over 32. Okay? Remember, pre-multiply, pre-multiply, post-multiply, post-multiply. So what's actually happening is, those two cancel off to give the identity matrix times xy, and then xy equals, you'll have to multiply that out. Remember how to calculate an inverse? If you have the matrix A, B, C, D, it's 1 over AD minus BC. Then the ADs swap and you change the sign of the other diagonal. Okay? I'm not going to go through all of that. I'm just pointing it out to you, and I'm sure you're more than capable of dealing with that. Okay. So, on to the next bit then. And again, the next bit is fairly straightforward. I'm going to write in red. Part 1. It's in blue. Part 1 says the modulus of Z1 is equal to 10. That's really, really straightforward. So what you're saying is the modulus of S plus 8I is equal to 10. Modulus means the square root of S squared plus 8 squared. Been a little bit fussy about how I set that up there, just making sure you put the imaginary part, or the coefficient of the imaginary part, put it in brackets. If it's a minus, it goes in brackets, etc. Equals to 10. You're going to square both sides, so S squared plus 64 is going to equal to 100. S squared is equal to 36. S is equal to plus or minus 6. Okay, really simple, really straightforward. You're given an indication or a little bit of a hint that there might be more values of S than just the one, because it says possible values. Alright then, on to the part 2. And this actually isn't all that difficult, it's more just how the question is worded. So A or G, what does A or G mean? Well, the argument means the angle. Right? In complex numbers, the argument, it's like the reference angle that you're using. Right? So really what they're saying is, if I were starting the question, I would say the tan of theta is equal to opposite over adjacent when I had plotted my complex number. Then I would get the tan inverse of the other side. I'm going to write all this out in a second. I get the tan inverse of the other side, and that would be theta, and that would be my argument. Okay? So what we're told is, we're told the argument of Z2 is equal to 3 pi over 4. Well, let's just leave that there just for a moment, and let's have a look. Let's talk about Z2. Z2 is t plus 8i. And that's what it would look like if I plotted it on an Argand diagram. And what I'd say then, or if I were to tackle that question a little bit further, I'd normally say, well, the tan of theta, well, the tan of rho, of course, but in this instance, because it's in quadrant 1, I can just say the tan of theta, well, that would be the opposite over the adjacent. So the tan of theta would be 8 over t. But if you look back here, they've already told me what the angle actually is. So in other words, the tan of 3 pi over 4 is 8 over t. If you do that in your calculator, that's it. Okay? Alright. I'm going to keep going, and I can come back to that if there's later on if there's questions. Alright. The C part. You're asked, use De Moivre's theorem to find in polar form the 5 roots of the equation. Now there's a couple of things going on here. First thing you need to notice is that it's a complex equation. And the mistake that people make, when you're dealing with complex equations, there's an order, basically like an order of operations, okay? So the order of operations is you put it into polar form, then you get the general polar, and then you apply De Moivre's. And the mistake that people usually make is that they get the two of them mixed up. They put it in polar form, then they apply De Moivre's, and then they try and get the general polar form and then sub in 0, 1, 2, 3, 4, etc., however many is needed. Now you'll know you've made that mistake if your answers are all coming out the same. Okay, so check your own work there. If you see that when you subbed in what's this, Z to the 5, so you just said 0, 1, 2, 3, 4, if all the answers are coming out identical, well then you know you've made that mistake. Okay? So what's there now is the proper order. So polar form, general polar form, and then apply De Moivre's theorem. So what are we told here? We're told that Z to the 5 is equal to 1. Of course that's 1 plus 0i. I'm going to ignore the left hand side, I won't worry about it for the moment, and I'm going to put this into polar form. So if I plot it on an Argand diagram, well, it'll be there. So theta equals 0 degrees. So Z to the 5 will equal to, and of course the modulus will be 1. Square root of 1 squared plus 0 squared equals 1. So it will be 1 cos 0 plus I sine 0. And there's the polar form. The next thing you need to do is get the general polar form. Don't touch the Z to the 5 for the moment. So Z to the 5 and I'll just stick this in red so you can see. There's different ways of doing it. I'm going to say 2 pi n. Just a little thing there, sorry, that should be 0 plus. Okay. Now 2 pi n, some of you may choose to use 360n. The only reason I'm doing that is because I'm asked to keep it in polar form. You can have your polar form, cos of 360, or you can have it in degrees as well. I don't know, it's probably better off just leaving it in radians. Okay, so what are you left with? Z to the 5, keep tidying. So you'll have cos 0 plus, so it's just going to be 2 pi n plus I sine 2 pi n. Z to the 5. Okay. Z, no, let's just take Z. Z is equal to cos 2 pi n plus I sine 2 pi n. All of that. Well, if it's to the power of 5 on the left, obviously I need to get the fifth root. Getting the fifth root of both sides is the same as putting both sides to the power of 1 over 5. And I'll just put this in red for you then, as I'm sure you know. The power comes down in here and multiplies. Comes down in there and multiplies as well. So Z is equal to cos 2 pi n over 5 2 pi n over 5, and that's you've done all. You know, first of all, you've got your polar form. General polar is with the 2 pi n, and now you've applied the Marvis theorem. It's to the power of 5, so that means there's going to be 5 roots. You'll start with n is equal to 0, n is equal to 1, then 2, then 3, then 4. Okay, I'm going to do that in the next page because I need a bit of space. Okay, so you're going to start subbing in your different values. So first value you'll sub in is n equals to 0. If n is equal to 0, well, in that instance z is going to equal to the cos. Well, if n is 0, everything is 0, so the cos of 0 plus I sine 0. And I'll stick the answers there maybe. You're going to get 1. Next thing, n equals 1. Z is going to equal to the cos of 2 pi over 5. And that's it. You don't need. There's nothing more to do as such. In previous years, you would have had to use the calculator just to evaluate that. But if you go back and read the question, it does say use the Marvis theorem to find in polar form. So it has to be in polar form. That's why I'm not changing anything. N is equal to 2. Z is going to equal 2. That's it. They're the 5 roots. That's part 1 done. Part 2 of the question then goes on and says, it says choose one of the roots w, where w is not equal to 1, so we obviously can't use that first one that we had, and prove that w squared plus w cubed is real. Okay. So I'm going to use this root here just because it's the next one down. Okay. So what do we try? We've got w squared plus w cubed, and our root is the cos. So it's the cos of 2 pi over 5 plus I sine 2 pi over 5, and I have to square that, plus the cos of 2 pi over 5 plus I sine 2 pi over 5, and I have to cube that. I'll go on to the next page now in a second just for more space. Now, some of you might then set about squaring out that first bit and cubing out the next bit. But if you slow down a second and just have a little look, you can apply the Marver's theorem. This is the whole point of the Marver's theorem, or one of them. So the 2 comes in and it multiplies. So the first bit, w squared, will be the cos. Well, 2 2's are 4, so it's 4 pi over 5 plus I sine 4 pi over 5 plus the cos of 6 pi plus I sine 6 pi over 5. Just going to turn over now for a second. Okay, so where does that leave us? Well, I'm going to group the reals with the reals. Handiest thing, into the calculator, evaluate them. The cos of 4 pi. Oh, there's an even better way to do this. Okay, even better way. There are properties. Plug it in. Or find another power source. Plug it in, though. Look at this stage, calculator. Right, just use a calculator. It'll turn out to be a real number. The real number happens to be 1. Okay, no problem. Right. You can look at it this way. This is interesting. This is just properties of complex numbers, and I'll just do it because it's cropped up, right? So sorry, let me just go back to cos of 4 pi over 5 plus I sine 4 pi over 5, and then you have the cos of 6 pi over 5 plus I sine. Now you can see there that they're kind of two different numbers, 2 in polar form. Shorthand notation. This is CIS, so C for the cos, I for the I, and S for sine. 4 pi over 5 added to, and this is CIS 6 pi over 5. And when you've got notation like that, there's a little rule. I'll just stick it here for you, right? The cos of, we'll say, theta 1 plus the CIS of theta 2. Well, there's a property that says that that's actually the same as CIS of theta 1 plus theta 2. So in other words, what I can say here is that this is 4 pi over 5, 6 pi over 5, that's 10 pi over 5, so it's 2 pi. So it's the cos of 2 pi, I sine 2 pi, and if you do that out, you'll still get 1. Doesn't make any difference which way you're going to do it, but I think it's interesting just from the point of view of the properties of CIS. Seeing as you're there, in terms of properties of CIS, you can do the same thing if you're asked to divide. Let me just turn over. So this is off the point on the question. The question is now finished. But if, for example, you had two complex numbers, something, I'll just make them. The cos of, let's say, 2 pi I sine 2 pi, and you were asked to divide that by the cos of pi I sine pi. Now, you don't need to convert it into CIS, you just need to be aware of the property. But being, as CIS 2 pi over CIS pi, there is a rule that says if you have CIS of theta 1, CIS of theta 2, that's the CIS of theta 1 minus theta 2. So you can just say top minus bottom. so it'll be the CIS of pi. Okay, now lads, just so as we're clear, because sometimes people get a little bit confused here, it's not that anything is cancelling here. Okay, sometimes people see the pi and they're cancelling. No, they're not, they're subtracting. It's kind of like indices. Okay, that's it.